Hello everyone and welcome. My name is Jason Gregerson, and this video is going to be about exact equations. What are exact equations? Well, they're differential equations that can be expressed in these two forms, either some function plus another function of x and y times y prime equals 0, or if we express that in differential form, we have f times dx plus g of xy times dy equals 0. And the equation is exact if there exists some function capital F such that the partial derivative of f with respect to x equals the first function f of xy, and the partial of big F with respect to y equals that second function g of xy. Now, if this is true, if the differential equation is exact, then we could rewrite those forms to look like this. Capital F sub x plus capital F sub y, where those subs indicate partial derivatives, times y prime equals 0, or once again in differential form as shown here. Now, if this differential is exact, if this differential equation is exact, then the solution is just whatever that capital F function is equals constant. So once we've shown it's exact, if we knew what this capital F function was, we could immediately write out the solution to be capital F of xy equals c. So the first question might be why? Why is the solution this simple and why must it have this form? And the answer we can really see by just verifying it's a solution. If this was a solution, we should be able to take the derivative and have it equal the original differential equation. So if I were to actually calculate the derivative with respect to x of this function of two variables in this case, well, from equals constant, well, then from calculus 3, to calculate the total derivative of a function of more than one variable, the result would be the partial with respect to x plus the partial with respect to y times dy dx, and the derivative of the right-hand side would be 0. So calculating this using our knowledge from multivariable calculus immediately yields the form of an exact equation. So, for example, let's say I was given the differential equation shown, y cubed plus 3xy squared times y prime equals 0. Now if we were given this differential equation, and if we looked at the function, capital F of xy, that was equal to xy cubed, then if this was to be an exact equation, I would need the partial of x to be y cubed and the partial of f with respect to y to be 3xy squared. And I can verify that by calculating the partial with respect to x. In this case, I'm treating y like it's a constant value. If I take a constant times x, and take the derivative with respect to x, I would just get whatever that constant value was. If I take the partial of f with respect to y, now I'm treating x like it's a constant, and really thinking of this as taking the derivative of some number times y cubed with respect to y. This would be 3xy squared. And so I can really see that this is the partial with respect to x, this is the partial with respect to y. So there does exist this function, such that these partials are equal to the little function f and the little function g, which means we can immediately write out the solution to the differential equation, which would just be f of xy equals constant. So in other words, the solution is xy cubed equal to constant. This would be our family of functions, family of solutions to the differential equation. So for example, if maybe we had an initial value condition, initial value problem, so I had this condition that y of 0 was 2 or something like that, well then I could also just plug that condition in here to find a specific solution. So we're really just writing out the solution of the differential equation once we know what this function f is. All right, so this really leads us to two key questions here for exact equations. One, given a differential equation, how do we know if there's actually going to exist the appropriate function capital F to make the equation exact? And then two, how do we actually calculate or discover what the function was? So these two questions are really related to the actual method of solving the differential equation. And here's going to be our answer. So given this differential equation that has this form, we're basically hoping that this first piece, that there exists some function where capital F sub x, the partial of capital F with respect to x is equal to f, and the partial of big F with respect to y is equal to this g function. Now if that was true, If there was this function that existed that satisfied that, this function would also have to satisfy a theorem from calculus 3, multivariable calculus, where the mixed partials were equal. And it turns out that condition is actually sufficient enough for this differential equation to be exact. So if f is supposed to be the partial of f with respect to x, then to calculate this left-hand side, I would just calculate the partial with respect to y of my f. And I would check to see, is that equal to the partial with respect to x of my g piece? And if those are equal, the differential equation is exact. So let's look at an example. If I had this differential equation, then to show that this differential equation was exact, I would have to take this first piece, which I'm hoping is the partial of f with respect to x, and calculate the partial derivative of that with respect to y. In this case, I'm treating x like it's a constant, taking the derivative with respect to y. In this case, I would get 2x. Next, I would look at the next piece, which I'm hoping is the partial of f with respect to y. Taking the derivative of that with respect to x would give me 2x as well. So here I can see that the differential equation is exact because the mixed partials are equal to each other. Next, to find the actual function value, I would start by taking my partial derivative with respect to x, that first function piece, and integrating it with respect to x. If I do a partial integration of this with respect to x, the result should be my first expression for f of xy, and the result here would be y times x squared plus x plus, normally I'd add my constant of integration, but because I'm doing a partial integration with respect to x, I wouldn't have a regular constant, I would have any function of just y. Because remember, to check my work after integrating, I could take the derivative and see if I get back to where I started from. But in this case, because I'm taking a partial derivative with respect to x, any function of just y would disappear when I'm calculating that partial derivative. So this is my first guess at my function, and really I just have to find this missing function of y. Now, one way I can do that is to look at my other piece up here, my f sub y piece, and if I integrate that with respect to y, I should get another expression for my function. When I integrate this with respect to y, I'll get x squared times y plus y cubed, plus I guess some arbitrary function of x in this case. But all I'm going to do is look through this new expression and try to identify the function of just y. In this case, it's just y cubed, and that should be my value for psi of y. That's my missing piece, the function of just y. See, I already have this term, the x squared y, already accounted for in my original calculation of f. The only piece I was missing is just the function of y. Now, I could have done this in the opposite order as well. For instance, if I would have started by integrating first the partial of y with respect to y, then I would have been trying to find my missing function of just x, which by looking at the other integral, I would find is just x here. So whichever order I do it in, the point is to do one first and then just look for that missing piece. When everything is said and done, now I can see that my function is yx squared plus x plus y cubed. And then my solution to the differential equation, remember, is supposed to be the function equal to a constant. So my final solution would be this guy equal to some constant. This is the general solution, the family of curves that satisfies the differential equation. All right, so if we just recap the high points here, the idea is given some differential equation, my first step was to check to see if it was exact. To do that, I calculate the mixed partials and see if they're equal to each other. Once they are, I know it's exact, and I go about finding my missing function here. So to do that, I first integrate little f here, the partial with respect to x, integrate that with respect to x. That will generate my first attempt at my function with that missing piece, and then I integrate the other piece with respect to y to discover my y function. I put it all together, and last but not least, my solution is f of xy equals constant. All right, that concludes this video. Thank you very much.